going on here. All right, so what I want to do today is I want to do integration without integration. All right, now we're going to have to do some integration at first, but by doing one integral, we will then be able to avoid a huge amount of integration from that point onward. I'm going to work with one of the most important probability distributions, the normal. And so fx of x will be 1 over 2 pi sigma squared square root e to the negative x minus mu squared over 2 sigma squared. We expect the expected value of x to be mu and the expected value of x minus mu squared to be sigma squared. If this is not the case, this is bad notation. Okay? So let's calculate these quantities. The mean is not so bad to calculate. So for the mean, we want to calculate the expected value of x. This is the integral from minus infinity to infinity of x times fx of x dx. I'm sorry? So if you notice, the integrand here only depends on x minus mu. So here's a really nice trick. We can write this integral as x minus mu plus mu times fx of x dx. And then we can split this into the integral from minus infinity to infinity of x minus mu 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx plus, this is a constant, so it just comes outside, and it's integral from minus infinity to infinity of fx of x dx. If we look at this part, this is a symmetric integral. It's a symmetric interval about what point? About mu. And this is an odd function. It's an even function here. It's an odd function here. So odd times even is odd. If you want, you could change variables, and you could replace x minus mu with u, and this would become a minus u squared. This would be a u. You'd have u going from minus infinity to infinity. This integral will just be 0. And what's this integral going to be over here? 1. So that's assuming we have the proper normalization constant, which we'll get to in just 1 second. So if we assume that this integrates to 1, we just get mu. So a lot of the integration for the mean we're able to bypass just by noticing, if we add 0 in a clever way. We still need to know that this is normalized to be a probability distribution, and that's where the square root of 2 pi is coming from. The other thing is, whenever you have integrals like this, you want to make sure things converge. So in the book, I go through at length talking about how we know this converges. Whenever you have convergence issues, you always wonder, is something blowing up? And if it's blowing up, you have to be careful about that. And then, is it decaying fast enough at infinity? So in terms of blowing up, well, we never have any places where we have a division by 0, so we're okay there. What about going off to infinity? Well, this is going off like e to the negative x squared. We know the function e to the negative x is integrable. It's decaying fast enough at infinity. This is decaying even faster for larger values of x. If x goes off to negative infinity, well, because we have an x squared, that's still going to be e to the negative something huge. So if you just do a little bit careful calculations, you see you have beyond exponential decay. So even if you put in a polynomial growth times exponential decay, you still have exponential decay. This is going to decay fast enough so that everything will be fine. The difficulty is now determining the normalization constant, as well as determining the second moment. I can't quite do this trick for the second moment, unfortunately, because the first moment just has this very nice x minus mu that vanishes because it's an odd function. And I'm then left with just a mu. For the second moment, the calculation is going to be a little bit harder. All right, so the first thing I want to do is the normalization constant. I'm not going to do the most general case as a really good exercise. I encourage you to do this. I'm going to assume mu equals 0 and sigma equals 1. You can get this by just doing a change of variables. Okay? So you could let u equal x minus mu over sigma. Du will be dx over sigma. And if you do this change of variables, calculating the normalization constant for the general Gaussian is now reduced to calculating the normalization constant for the standard normal. This is a common theme. Rather than doing the more general case, try to do a simpler case and just see how they translate. If you think about it, all we're doing here is we're shifting all the values of x by mu. So we should be shifting the mean by mu. If I add 5 to every value, the mean shifts by 5. If I divide by sigma, I'm changing my scale. Rather than measuring things in feet, I'm measuring things in meters. And we know how the means and the variances change. These are not going to change the functional form. And this is going to be a huge part of the lecture later today. What's the functional form? A shift like this is not changing the functional form, it's just changing the scale. If you don't like this argument, by all means do the calculation in full generality. This is to just justify it's enough to study mean 0, variance 1, and you can then just apply this transformation. All right, so now let's calculate the normalization constant. So we want to integrate from minus infinity to infinity e to the negative x squared over 2 dx. Okay? So we want to calculate this. What do you think this integral should equal based on what we've written as the density of the normal? What should this equal? Square root of 2 pi. So let's let I for integral equal the following. We don't have that many tricks for multivariable calculus. We have change of variables, and we have changing the order of integration. Now, this is not necessarily a good time to be talking about multivariable calculus. Why is this a bad time to talk about multivariable calculus? I'm sorry? We only have one variable. All right, well, let's remedy that. Let's look at I squared, which is the integral from minus infinity to infinity e to the minus x squared over 2 dx, integral minus infinity to infinity e to the minus y squared over 2 dy. I'm using a different variable for the second time. The dummy variables of integration. What can I do now that I have two variables like this? So it's the integral minus infinity to infinity e to the negative x squared plus y squared over 2 dx dy. And there's so much decay, there's no problem with looking at this integral. Why is this a good thing to do? Well, you don't want to integrate e to the negative x squared over 2 dx. What would you love to have in front of the dx? An x. Can you just throw in an x? No. But notice that when we look at this square of the integral, we have e to the negative x squared plus y squared. In polar coordinates, x squared plus y squared is r squared. And then dx dy becomes r dr d theta. How many of you have seen this trick in multivariable calculus? Okay, some of you have. So we'll let x be r cosine theta, y be r sine theta, dx dy becomes r dr d theta. You should really view this as r d theta times dr. And the reason is the angle has no length. Dx dy, this is an area. This is like meters squared. I should view this as the arc of length r d theta times the radius, which infinitesimal radius change. X squared plus y squared is just r squared cosine squared plus r squared sine squared is r squared. And we get I is equal to the integral. So let's see, we have r dr d theta. So r is going to go from 0 to infinity. Theta is going to go from 0 to 2 pi. And that will expand and give us the entire plane. E to the negative r squared over 2 r dr d theta. So we have two integrals to do. We have the theta integral. Yes?
Isn't it I squared?
Yes, thank you. It's I squared. Thank you. So we have two integrals to do. Which is the easy integral to do, the theta or the r? The theta. What does the theta integral give us? Gives us 2 pi. You can begin to see where the square root of 2 pi is going to come from, given that I squared equals 2 pi. And now we have the r integral. And boy, is life good. What's the derivative of e to the negative r squared over 2? E to the negative r squared over 2, and we'll have a negative 2r over 2, we'll have a negative r. So what we need, if we want to do a u substitution here, is if we let u equal r squared over 2, du is going to be negative r. The negative sign is going to flip the order of integration, and we'll get e to the negative r squared over 2 at 0 and infinity. Well, if we put in infinity, we have e to the negative infinity squared. Even dividing by 2, that's still going to be 0. And then we have e to the 0, which is 1. So we get I squared is 2 pi. So what do we know about I? I'm sorry? Why can't I be negative square root of 2 pi? Yeah, we know I is greater than or equal to 0. And because we know I is greater than or equal to 0, we're integrating a positive function. We can't have the negative square root surviving here. So this is the one integral we really need to do today. Okay? This gives us the normalization constant for the standard normal, the normal with mean 0, variance 1. If you wanted to do the more general case, if you want to do x minus mu, if you want to divide by 2 sigma squared, you would just have the sigma squareds propagating through. That would change the integration here a little bit. You'd get a sigma squared coming out over here. Yes?
Why did we change infinity to 0? Like 0 and infinity?
Because we have an e to the negative r squared over 2. So if we let u equal negative r squared over 2, du is going to become negative r dr. And now as r goes from 0 to infinity, what's the range of u? So a lot of it depends on where you want to define things. I'll probably define things maybe like this. If I do it like that, u will still go from 0 to infinity, but now I'll have an e to the minus u. And when I have an e to the minus u, if I integrate, I'm going to have a minus sign coming down.
Okay.
So just when you do the integration by parts, you will flip the order of integration. So again, you should be comfortable doing integration at this level. If you're having trouble with this, by all means, there's practice problems in the end of the book. I'm also happy to meet with you and go over some of the integrations. But this is something that's supposed to be already known for this class, integrating by parts. I will not give you painful partial fractions. Right? But I've got to keep integration by parts. I've got to keep u substitution. These are the things we need to be able to use. Okay, any questions about this calculation here? Yes?
We go over like deriving dx and y equals r dr d theta.
If there's time later today, I will do that. That's too much of a Math 150 question to go into why this is that. That's something you're supposed to have done here. Okay. Other questions about this calculation? Okay. So now that we have this, we want to go back and we want to try to calculate other questions, other quantities of the normal distribution. So let's go back and let's look at the standard normal. So for the standard normal, sigma is going to be 1 and mu is going to be 0. So we will have f of x is 1 over square root of 2 pi e to the negative x squared over 2. We want to calculate the expected value of x squared. And because it's the standard normal, because the mean is 0, this is also equal to the variance. And I'll put an x subscript to remind myself it's the variance of the random variable x. So I want to integrate from minus infinity to infinity of x squared 1 over square root of 2 pi e to the negative x squared over 2 dx. Okay. Unfortunately, we don't have much luck integrating e to the minus x squared. There's no nice antiderivative for that. But we do have the function x squared. So you should be thinking integration by parts. Now, when you're thinking integration by parts, you have to choose what do you want to be u and what do you want to be dv. So do I want to be integrating x squared to x cubed, or do we want to be differentiating x squared down to x? It seems to be natural to differentiate x squared down to x, lower the degree of x squared. And maybe if we just do this twice, we can go from an x squared to an x to a constant, and we know the integral of e to the minus x squared from minus infinity to infinity. Yes?
Can we just break up the x?
Yeah. So we're going to get to that in just 1 second. So does it make sense that we would want to break down the x squared to x to 1? The problem with that is if we put x squared as u and then du as 2x dx, that means dv would have to be 1 over square root of 2 pi e to the negative x squared over 2, which means we would need the antiderivative of that. And then we would have to integrate the antiderivative of that. We can't do that. However, if we wanted to integrate this, what piece would make this a lot nicer?
The x.
The x. You can see this is screaming, I want an x. Right? Because if it had an x, then we could integrate. So if we put an x there, then this x squared just becomes, well, that's fine. That makes our life even easier over here. We'll only have to do this once. So now when we integrate this, what function has this as its derivative? E to the negative x squared over 2 with a negative 1. And now when we take the derivative, we'll get this piece back, and then we'll get a negative 2x over, we'll get a negative x. And the negative reinforces with this. So now when we do our integration by parts, we get uv at minus infinity infinity minus the integral from minus infinity to infinity of v du. And again, you need to know integration by parts. The boundary terms are going to vanish. uv, I'm going to have x, and I'm going to have e to the negative infinity squared. The exponential decay kills the polynomial growth. This term is just going to be 0. The negative reinforces with the negative, and we get the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the negative x squared over 2 dx. Oh, that's nice. What does this integral equal? 1. So this is a proof of how to calculate the variance of the standard normal. If I were to replace the 2 with the 2 sigma squared, how much would things change? Well, let's see. This is the advantage of being at the blackboard. I can add the sigmas very easily. I put the sigmas in there. So now I come over here. I've got a sigma squared down here. I have a 2 sigma squared over here. I have a 2 sigma squared here. I have a sigma squared down here. I have a sigma squared over here. Now, what happens when I take the derivative? Is my v correct now, or do I have to change it a little bit? Is this v correct for this as my dv? I've got, if I take the derivative of this, the negatives will reinforce, the 2 cancels with the 2, but I get an extra 1 over sigma squared down below. The derivative of this is not dv. I've got to fix this. What do I do to fix this? Multiply by sigma squared. And if I multiply by sigma squared, now the derivative of this v will be what I want. And so now when I come over here, the minus signs still reinforce. I've got a sigma squared down here. I have a sigma squared over here. I have a sigma squared over here. I pull the sigma squared outside of the integral. And now I'm just left with the integral of the density, which is just 1. So now I get sigma squared. So you can see it's not that bad to put in these extra factors. This is a calculation of the second moment. How would we calculate the third moment? Well, the third moment won't be that bad. It would be an odd function. What about the fourth moment? What would we do? Same integration by parts. Okay, so let me list the first couple of moments. Okay, it's at least turning. So, standard normal. Moment value. First, second, third, fourth, fifth, sixth. The first moment is second moment. Third moment. Fourth moment, I'll do that. It's 3. Fifth moment. Sixth moment. 15. Anybody recognize these numbers? Double factorial. The 2kth moment is 2k minus 1 double factorial. There's a huge combinatorial significance to this. Something deep is going on. It comes down to matching things in pairs. You know, this problem that you were given earlier in the semester about the double factorial. As mathematicians, we can define almost anything we want. Most definitions will not be useful. What is another definition for the double factorial? It's not the one we have agreed to use, but if you were just naively looking at double factorial, what would you think double factorial meant? The factorial of the factorial, right? The double factorial should be the factorial of the factorial. Why is the factorial of the factorial not this meaning? I'm sorry?
It's way too big.
It's not that it's way too big.
Not as useful.
It's not as useful. So it turns out that in the problems we study, the factorial of the factorial does not really come into play that often. But the product of every other, that does come into play a lot. One of the reasons it comes into play so many times is because of the normal distribution. You have the central limit there. You don't get the word central for nothing. Okay. So one way you could try to prove this in general is you could do something by induction. Okay? And if you want to do this by induction, what you would then do is you would calculate, you would assume you know the 2kth moment, you would look at the 2k plus second moment, you would split things up similarly like this. This would become an x to the 2k plus 1, you would have an x over here, you'd play the whole game, and you would do the argument. So if you want, this is a really good proof by induction to do. There is another way to do this. What other technique do we have for calculating moments of probability distributions? Differentiating identities. So what I want to do is I want to talk about how you would prove this using differentiating identities. Okay? If we're going to use differentiating identities, what do we need to start with? An identity, and we need something to differentiate. So if at the end of the day you only care about the standard normal, it's not enough to just look at the standard normal. You have to embed the standard normal in a family of distributions. Okay? This is a really important concept. You can read the algebra at home. You can go through the calculus at home. If you have trouble, come see me. I really want to emphasize at a deep level what's going on, why does all this work. At the end of the day, if I only care about the standard normal, if I want to use differentiating identities, I need to have a parameter. What do you think my parameter is going to be? What should my parameter be? There's not that many parameters in play when you look at the normal. We have the mean and we have the variance or the standard deviation. It's the standard deviation that's going to be our free parameter. The mean just translates things. The mean is not that important. But the standard deviation is going to come in very nicely. So let's look at this as our density. So if we want to use differentiating identities, we know, and I'm going to rewrite this in just a moment, that the integral from minus infinity to infinity of 1 over the square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx equals equals 1. I'm going to move the sigma squared over to the other side just so that when I differentiate, I don't have to use the quotient rule. It just makes the algebra nicer. I could start with this and apply the operator d by d sigma. But if I move the sigma squared over to the other side, I don't have to worry about the quotient rule. I don't like using the quotient rule. Okay? I want to minimize my chance of making an algebra mistake. So I'm going to start with sigma squared is the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the negative x squared over 2 sigma squared dx. Now, at the end of the day, I cannot interpret this as integrating something against a normal density. I'm missing a 1 over sigma because I should have a sigma squared under the square root. That's not a big deal. After I'm done differentiating, I can always multiply by 1 over sigma to both sides. Let's look and see what would happen. What if we differentiate both sides with respect to sigma? What's going to come down? It's okay if you don't give me the whole thing correctly. What comes down when I take the derivative with respect to sigma? I'm sorry? The x squared. Ah! And if an x squared is coming down, that's exactly what we need to get the second moment. If we differentiate with respect to sigma, an x squared pops down. Then the rest is just doing some algebra so that you end up getting the integral of x squared against the normal's density. So you'll have to play some games with multiplying by sigma. But the advantage of this is you don't have to see the clever integration by parts. The natural thing when we were looking at the integration of parts was to take x squared as our u. And we ran into trouble, and then fortunately we had a suggestion that we should move one of the x's and split things up. This allows you to bypass having to see that.
Sigma equals because it's a square.
Oh yes, sorry, yes, thank you. That should be sigma because we've got it under the square root. Thank you. So we get sigma equals this. So now the question is, what operator should we multiply both sides by? We should take the derivative with respect to sigma, and then do we want to multiply by sigma afterwards? I don't know. Haven't done the calculation. Okay, I have done the calculation. I'm going to pretend I don't know right now if I want to apply just the derivative with respect to sigma or sigma times the derivative with respect to sigma. We'll find that out after we apply it. So let's apply d by d sigma. All right, the derivative of sigma with respect to sigma, 1. The derivative of the integral is the integral of the derivative. We can switch the order. Okay? Again, which class justifies this? Real analysis. If you haven't taken it, please do so at some point. You'll be able to justify interchanging orders. We have so much decay here, not a problem. So the integral of the derivative is the same as the derivative of the integral. So we get the integral from minus infinity to infinity, 1 over square root of 2 pi, and now we have e to the negative x squared over 2 sigma squared. Now we have to take the derivative of this. All right, this is really 1/2 x squared sigma to the negative 2. And we actually have a negative here. So when we're taking the derivative by the chain rule, it's the exponential of blah times the derivative of blah, right? What do we get? We have a minus 1/2 x squared, and then we'll get a negative 2 coming from the sigma squared, sigma to the negative 3. Okay? So the negative and the negative reinforce. We get 1/2 2 x squared 1 over sigma cubed dx. Okay. What's 2 times 1/2? That's just going to be 1. The sigma cubed, how many sigmas do we want to keep on this side? 1. We need to have a square root of 2 pi sigma squared. We need to keep a sigma on this side to come into the square root. So that means we have to move sigma squared over to the other side. And so we get sigma squared is the integral from minus infinity to infinity, 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. Oh, and we still have that x squared floating around, which is exactly what we want. And there is the second moment. So we can do the second moment now Very easily. If we wanted to do the fourth moment, could we do that? Now, if we were going to do the fourth moment, what would you want to do first? Would we want to take the derivative of both sides right now? No, because I'd have to use the quotient rule. What would I do before I take the derivative again? Multiply by sigma cubed. So I had sigma cubed equals this. And if I take the derivative of sigma cubed, I'll get 3 sigma squared. And then I'll have another sigma cubed coming over. Then I bring this over, and I'll get a 3 sigma to the 5th. When I take a derivative of 3 sigma to the 5th, what will I get? 15, also known as 5 times 3 sigma to the 4th. And then I'll have another sigma. So you can keep seeing this is why you're getting the double factorials. So it's a nice exercise. Go through and see how you can get double factorials from all of this. Yes?
When you're saying apply d by d theta, is that
d by d sigma.
is that multiplying it by?
No, it's applying the operator to both sides. So taking the derivative of both sides with respect to sigma.
Okay.
So I have this identity. And because this is an identity, if I apply d by d sigma to both sides, it still holds. Yes?
How is it sigma cubed over there and then?
Well, if you look, this is the exponent, right? It's negative 1/2 x squared sigma to the minus 2. When I take the derivative with respect to sigma, the derivative of sigma to the negative 2 is negative 2 sigma to the negative 3.
Okay.
I'm just using the definition, the standard power rule formula.
Okay. So when you bring it down and then you multiply both sides by sigma cubed.
I'm not multiplying, well, right now, I'm moving a sigma squared over to the other side, and I'm leaving a 1 over sigma. And the reason is I need to have a sigma squared inside the square root. Well, if it's a sigma squared inside the square root, I need to leave a 1 over sigma. The reason I need that is because this is my probability density function. If I want to claim that I have the second moment, I need to be integrating x squared against the density. I must have a sigma squared down below. What I'm doing here is by knowing one integral, we're getting all these others. So when we did the other method, when we did integrating by parts, that was much harder. We had to be clever. We had to figure out how do you move things. Right now, we are milking this one integral. And we can just keep milking this and get everything we want now. Okay? Any questions on this? What I want to do now is I want to continue integrating without integrating. I want to calculate sums of 2 normal distributions. In general, if you do anything, the more times you do it, the more of a mess it is. If I take a uniform distribution, and I take another uniform distribution and add them together, is uniform plus uniform uniform if they're independent? Okay, give me an example where uniform plus uniform is not uniform. I'm sorry? Rolling a dice. In fact, what kind of shape do we get if we do uniform plus uniform? We get a triangle. So in general, if you have a distribution and you take 2 independent copies of it, you're not going to get the same thing back. Have you seen anything in any of your other classes where it's really special and you have a special name where if you apply this operator, a lot of your properties are left unchanged? I'm sorry? You've done this in a class. Linear algebra. What special word do you have in linear algebra? I'm sorry? Not idempotence. It's a special type of vector. Eigen Vectors. You apply your operator, right? You apply your operator. The magnitude can change, but not the direction. Okay? Eigen Vectors are extremely useful. In linear algebra, you should hopefully have seen lots of applications of Eigen Vectors and eigenvalues. The principal axis thing. You can decompose operators. You can find better bases to understand things. In general, in probability, if you take 2 probability distributions, if they're the same, and you add 2 independent copies, you get some mess coming out. The central limit theorem says if these distributions are nice, the more of them that you add together, the more it's going to look like a normal distribution. There are a couple of very special distributions where if you take two copies of them, independent, and add them, you get back something of the same shape. I'm not going to say exactly the same, because that would be bull. That should not really happen. If I have two random variables with mean 0 and I add them, what should the mean be? 0. What about the variance? Do you think the variance would be the same, larger, or smaller? There's only one way the variance will not be larger.
They're negatively correlated.
No. If the variances are both initially 0, right? I can have two independent Mobius coins. These coins always land on heads, right? And then they have no variance. And if I add them together, the variance of the sum is the sum of the variances. Well, the variance of each is 0. The sum is 0. In general, for any distribution you look at in the real world, you're going to have some variance. You're going to have some fluctuations. So the variance of the sum will be the sum of the variances. The variances will grow. I don't expect to have exactly the same distribution coming out, just because the variance has to grow. So you have to lower your sights. And again, I really want to emphasize what you should be gunning for when you do stuff like this. You should not be thinking normal, standard normal plus standard normal is standard normal. There's no way that should be true. So what's the mean of a standard normal? 0. Okay, and what's the variance of the standard normal? So if we use n0 sigma squared to represent a normal with mean 0 and variance sigma squared, what do you think this should be? A normal with mean 0, variance 1, plus an independent normal with mean 0, variance 1 should be normal with mean and variance 2. That's the result we can expect it to hold. Okay, it's too much to expect it to be normal 0, 1, but not by much. This is just a really minor tweak that all we have to do is remember the variance has to scale. Okay, so very few distributions satisfy property like this, where shape plus the shape equals the same shape. These are called stable distributions. There are three major stable distributions. One of them is the normal, and we'll prove that in a moment. There is another that we have met, and this is extremely important in economics, the Cauchy. The Cauchy is actually a stable distribution. What's the variance of the Cauchy? We agree the Cauchy has no mean, no finite mean. What's the variance of the Cauchy? Or the expected value of x squared. What's the second moment of the Cauchy? So the second moment of the Cauchy is infinity. Remember, the Cauchy is 1 over pi, 1 over 1 plus x squared. For the mean to exist, if I integrate the absolute value of x times the density, it has to be finite. You can argue whether or not this has a finite mean, because at least it's odd, but it definitely does not have a finite second moment. If I integrate x squared times this, the integrand is converging to 1 over pi. Maybe Cauchy plus Cauchy is the same Cauchy. We'll leave that for later. There is one other distribution that often is talked about, Levy distribution, but it is very rare to have something that's stable, where you have the same shape coming out. What I want to do now is I want to show to you that normal plus normal is normal. And the way we're going to do this is we're going to integrate without integrating. Okay? So normal plus normal is normal. What's really nice about this is if I can show that the sum of two normals is normal, what's true about the sum of three normals? Normal. What do we use to do that? Grouping. So by grouping, if we can show normal plus normal is normal, then we get normal plus normal plus normal is normal. Okay? So we really only have to prove that two normals sum to a normal, and then everything else is done by grouping. We might as well assume the means are 0, because all that will happen otherwise is we'll just change the variance. If you want, I will do the special case of normal 0, 1 plus normal 0, 1 is normal 0, 2, just to keep the notation a little bit milder. And then if you want, you can go through and put in the sigma 1s and the sigma 2s later. Or if you want, I'll put the sigma 1, sigma 2 on the board and just have it a little bit more cumbersome. First loud voice wins. All right, you want sigma 1s and sigma 2s? We'll do it that way. All right, so xi will be 1 over square root of 2 pi sigma I squared e to the negative x squared over 2 sigma I squared. Let's let z be x1 plus x2. And for those of you who do not like the algebra that follows, you should have spoken louder and first. Okay? How do we calculate the density of x1 plus x2? Convolutions. So we can go f of z is the integral minus infinity to infinity of fx1 of t fx2 of z minus t dt. So far, so good? All right, let's do the integration. We have the constants that we can pull out. So we're going to get a 1 over 2 pi sigma 1 sigma 2 when I pull out all the stuff over here. I will then have an integral t goes from minus infinity to infinity of e to the negative t squared over 2 sigma 1 squared plus z minus t squared over 2 sigma 2 squared dt. And I'm just combining the exponents. Okay? So we need to do this integration. Does this look like a fun integral to do? No. Now, if you know complex analysis, there are ways to do this, but we're not going to take a detour to do complex analysis. We already have enough stuff we need from real analysis, which is a prerequisite. There is a way to evaluate this without doing the integration. And we're going to use one of the most fundamental facts about a probability distribution. If I tell you I have a probability distribution, you know 2 facts immediately. What are those 2 facts? It's always positive, and it integrates to 1. So here is what I want to do. And we're going to use this idea time and time again. This is a major idea of the course. All I need to do is figure out the z dependence here. I don't, being recorded. I do not care what the t dependence is because we integrate out t. It's going to just give me a constant. All I have to do is pull out and understand what's going on with respect to z. Okay? So let's look at what's going on here. We have t squared over 2 sigma 1 squared plus z minus t squared over 2 sigma 2 squared. All right, so we're going to have to start doing some algebra here. Let's start expanding things out. We get t squared over 2 sigma 1 squared. And this is all in the book if you don't want to write it. Now over here we'll have a z squared minus 2zt plus t squared over 2 sigma 2 squared. Okay? All I care about is the z dependence. I have a z squared over 2 sigma 2 squared plus, all right. So if we now, everything has a 2 down below. I have to multiply this by sigma 2 squared and this by sigma 1 squared. Thank you so much for having me have unequal things. I will get sigma 1 squared plus sigma 2 squared times t squared minus 2z sigma 1 squared t over 2 sigma 1 squared sigma 2 squared. Have I made any mistakes? Please be watching the algebra. Yes?
What do you mean by the z dependence?
So when you look at this integral over here, it depends on z and it depends on t. But I integrate out t, so at the end of the day I'm left with a function of z. I claim that this is supposed to be a normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. So I actually know what this integral should be. It should be 1 over square root of 2 pi sigma 1 squared plus sigma 2 squared e to the negative z squared over 2 sigma 1 squared plus sigma 2 squared. All I need to do is detect the z dependence. If I'm then left with a nasty integral over t, that's going to be my normalization constant. So I don't need to evaluate the t integrals. I just need to know the t integrals converge. When you look at this, what is this beginning to look like over here? This part over here. What do we have? It looks like what?
A square.
It looks like a square. So we want to complete the square. So we're going to have z squared over 2 sigma 2 squared plus, I'll pull out a sigma 1 squared plus sigma 2 squared over 2 sigma 1 squared sigma 2 squared. And now we'll have t squared minus 2z sigma 1 squared over sigma 1 squared plus sigma 2 squared times t. Well, what do I want to put in here to make this nice? I want to complete the square. So I would want to add, I have a 2 here, so I want to put in, I think, a z sigma 1 squared over sigma 1 squared plus sigma 2 squared. And I think I want a square root of this. Well, no, okay. And then I have to subtract it, right? Z sigma 1 squared over sigma 1 squared plus sigma 2 squared. Have I made a mistake?
Should it be
Z squared. Z squared.
Probably. Yes, because I'm, okay, good. So this should be a z squared.
And sigma just like 2 whole squared.
Oh, this whole thing should be squared? Okay, okay, yes. Yes. Good, there we go, yes. And now, when we take this, we're going to write this as t minus this squared. And now I'll get twice this piece, which will be that over here. Excellent. And so now, the nightmare continues. Z squared over 2 sigma 2 squared plus, we have this whole mess over here, sigma 1 squared plus sigma 2 squared over 2 sigma 1 squared sigma 2 squared. And now we're going to have t minus blah of z. I don't even want to bother writing that again. Just some function of z. And it's going to be harmless. Right? We square that. And now we also have to subtract off this part. Minus z squared sigma 1 to the 4th over sigma 1 squared plus sigma 2 squared squared. But we have to multiply by sigma 1 squared plus sigma 2 squared over 2 sigma 1 squared sigma 2 squared. Notice that the t dependence is now localized to this part. This part only depends on z. This part does depend on z, but I can change the variable of integration for t. I can shift t by blah. You know, t ranges from minus infinity to infinity. If I shift t, am I going to change the value of the integral? No. So when the dust settles, our integral for fz of z is going to be the following. So we have a 1 over 2 pi sigma 1 squared sigma 2 squared. We pull out a this and we pull out a this. All right, so if I take this, that cancels this. If I take a sigma 1 squared, that reduces this from a 4 to a 2. we have a 2 sigma 2 squared, we have a 2 sigma 2 squared. If I made an algebra mistake.
You have an extra factor in the denominator. Sigma 1 squared plus sigma 2 squared.
Okay. We still have a sigma 1 squared plus sigma 2 squared. So we multiply this by sigma 1 squared plus sigma 2 squared. And you can begin to see why I wanted to simplify the algebra. Okay, so now they both have a 2 sigma squared. We have a sigma 1 squared over sigma 1 squared plus sigma 2 squared. We multiply this by sigma 1 squared plus sigma 2 squared over sigma 1 squared plus sigma 2 squared. We then subtract. The sigma 1 squared cancels with that sigma 1 squared. We're left with a sigma 2 squared. We have a sigma... and I think that sigma 2 squared will then cancel with the sigma 2 squared down there. And so when the dust settles, we'll have an e to the negative, dear God, z squared divided by 2 sigma 1 squared plus sigma 2 squared times the integral t goes from minus infinity to infinity of e to the negative t minus, we've shifted things, so it's going to be e to the minus t squared over blah dt. And whatever this is at the end of the day is some constant. Okay? The t integral is going to give us some constant c. And so at the end of the day, we get fz of z is some new constant c tilde e to the negative z squared over 2 sigma 1 squared plus sigma 2 squared. This constant is whatever this t integral is times 1 over 2 pi sigma 1 squared sigma 2 squared. What does this look like over here? This looks like a normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. So we know the normalization constant for that has to be 1 over the square root of 2 pi sigma 1 squared plus sigma 2 squared. We could get this if we wanted by actually doing this t integral, seeing what comes out, and then combining that with this. But the great thing is that we don't have to do this, is we actually get the result for free. This is a probability distribution. It must integrate to 1. Therefore, the normalization constant has to be whatever we need if we can detect the functional form. We only need to detect the functional form well enough to know that it is a normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. We then get this for free. This is integrating without integrating. Okay? It would have been a little bit nicer if we didn't have the sigma 1s and the sigma 2s, but this does show you the more general case. It's not so bad to see that. All right, so this is definitely a good place to stop. And then we will have one more class at most on special probability distributions, and then we'll start moving into Stirling's formula and then limit theorems. Okay.